And folks in the chat hear me okay? Wonderful, thank you. So as always, don't forget the seating survey. The only assignment for this week is preparing for the third midterm exam, which is going to be released on Wednesday this week. I'm going to go ahead and leave it open until Sunday, but if I'm having it available earlier so that students that want to take it earlier so that it doesn't bleed over into your holiday, you can do so. I am intending to have extended office hours during the day on Thursday, Friday, and Saturday. I do not know the specific times yet, but I expect it will probably be very similar to what I've done in the past, usually going from about 9 or 10 a.m. until about 4 p.m. There may be some meetings or things during the day that I will have to not be holding them during. I will post that information as soon as I have it. Are there any logistical questions before we get into content? I will take that as a no. Okay. So we have a pretty good list of Muddiest points that we can go over, covering a variety of topics. Let me get up and running. Okay. So we're going to start with some questions on ICE tables in general. A sort of logistical question about ICE tables on the exams. Will the problem specifically ask you to use an ICE table, or you need to interpret when to use it? You will need to interpret when to use it. This is looking not fully focused. All right, I guess that's the best it's going to get. So you're going to need to interpret when to use it. How do you know when to use an ICE table? So the idea of an ICE table is that it captures the reaction stoichiometry as a reaction proceeds to equilibrium. And so if you have a system that starts away from equilibrium and then, or perhaps was at equilibrium and then was perturbed in some way, and then you need to know something about it when it reaches equilibrium, that's when you use an ICE table. Now, the Henderson-Hasselbalch equation is essentially a specialized ICE table without having to write down the entire table. It is a case where that is specific for a weak acid buffer system in the region where you are close to equal amounts of the acid and its conjugate base. By close to, what I'm meaning there is typically if one component is 10%, the other component is 90% of the system, or vice versa. Anything between that range, you typically can use the Henderson-Hasselbalch equation. If it's outside of that range, then you often need to use an ICE table instead. The reason for that is that in the Henderson-Hasselbalch equation, it makes the assumption that X, the extent of reaction that you are shifting as you go to equilibrium, is going to be small and therefore can be neglected in the calculation that you're doing. So if you are more than about, if the difference between the two components, the acid and its conjugate base, is greater than the range that I listed, then typically the X can't be fully neglected, and so you need to go through the ICE table and use the more extensive version of the equation that you end up solving. So does anybody have any clarifying questions on when to use ICE tables, when to use the Henderson-Hasselbalch equation, or anything related to that? So basically, anything in that region. Okay. So a more detailed question, what do you do in an ICE table if you don't have all of the information? So I think this comes from a variety of Newton problems where you are told, for example, that let's suppose you have a reactant, another reactant, and it's going to be in equilibrium with this, and you're told a concentration of this, you're told a concentration of this, but you're not told a concentration of this. And so in my view, that is a poorly worded question because you should be given the information here. But in many cases in the Newton problems, you have to assume that since you're given concentrations of this and you're not given a concentration of this, that you're starting with 0 of it. Generally, I will make certain that on the exam in these cases that I make clear that, that concentrations are 0 where they need to be assumed to be 0. Okay. Anything else on ICE tables in general anybody would like me to clarify before I get into specifically acid-base stuff? Random question, do we need to do Piazza this week? Yes, there is you can do participation on Piazza this week and get points for that. Will there be shifted initial on the exam ICE table? Yes, you need to know how to do the shifted initial concepts, absolutely. Okay, let's talk about acids and bases specifically. How do you tell the difference between an acid and a base from the chemical formula? Okay, so there are two ways to think about this, and it's largely coming from the Arrhenius definition and the Bronsted-Lowry definition. If you are talking about a substance and whether it is an acid or it is a base, then what you are in isolation, then what you're looking for is something that produces the hydronium ion and something that produces the hydroxide ion. So, for example, if you have sodium hydroxide, well, it has the hydroxide ion in it, and we know that this is ionic, so it dissociates, and so this ends up producing the OH minus aqueous ion, and so we would call this a base, and in fact it is a strong base. For an acid, it is something that donates a proton in solution, and so produces the hydronium ion if you put it into water. And so something like HCl, which we know dissociates and produces the hydronium ion, you know that that is an acid. Now, mostly though, we use the Bronsted-Lowry definition of proton donor and proton acceptor. So if we have if we are given a reaction for, let's see, what can I do? So if we do, I don't always want to use the same ones. So let's say H2CO3 plus H2O is in equilibrium with HCO3 minus plus H3O plus. We can see that these two substances here are essentially the same substance, just with or without one of the protons. And we see that this substance is essentially the same as this substance, just with or without an extra proton. So what is happening in the process as we go from left to right is that a proton is being transferred from H2CO3 to H2O. And so what we have over here are the same substances, just with the proton in the other place. So this is acting as a proton donor, and therefore it is a Bronsted-Lowry acid in this reaction. This is a proton acceptor, and so it is the Bronsted-Lowry base in this reaction. If we think about the reverse reaction, going from the products to the reactants here, then what is happening is that a proton is getting donated from the hydronium to the bicarbonate. And so if this is the donor for the reverse reaction, then this is acting as an acid in this reverse reaction. And this is an acceptor of the proton, and so is acting as the base in the reverse reaction. And so what we have is a pair of compounds, a pair of species here that are called a conjugate pair. And so on one side, it acts as the acid. On the other side, it acts as a base. So we would say that carbonic acid's conjugate base is bicarbonate. Similarly, we have the water and its conjugate acid. Water is acting as a base, and its conjugate acid is the hydronium ion. So identifying the acid or the base comes, typically in a reaction, comes from looking at what the protons are doing and seeing what has donated and what has accepted in the course of it. Are there any questions here about being able to identify acids and bases and conjugates and such? Okay. So there was a question from Newton that somebody wanted me to go over. A weak acid strong base titration where 37.5 mils of 0.1 molar sodium hydroxide is added to 10 mils of 0.1 molar acetic acid. What's the pH going to be? Okay, so this one, let's look at what we are dealing with. So 37.5 mils of 0.100 molar NaOH and 10.0 mils 0.100 molar CH3COOH. So acetic acid here. So the first thing to do is to notice that we have a weak acid and a strong base, but the weak acid we have less of. And so as a result of this, we are going to end up being in the regime where we just have strong base. All of the acetic acid will have been protonated by that point. So what we need to do to find the pH is very simply to figure out how much excess sodium hydroxide we have after it has reacted to protonate all of the acetic acid. So we have 37.5 milliliters of NaOH, 1,000 mils is 1 liter, and we multiply by our concentration, which is 0.100 moles of sodium hydroxide per liter, and that's going to tell us how much sodium hydroxide we have. So get my calculator up. So 37.5 divided by 1,000 times 0.1. So we have 3.75 times 10 to the minus 3 moles of sodium hydroxide. And because it's because of the stoichiometry, that's moles of hydroxide that we have put into the solution. How much acetic acid did we have? Well, we do exactly the same thing, but with the different concentration. I'm just going to abbreviate this as HA for our acid. 1 liter, 1,000 mils. We use our concentration. So 10 divided by 1,000 times 0.1 gives us 1.00 times 10 to the minus 3 moles of HA. So if this is how much HA we have, and we are reacting the hydroxide with it, then the amount of hydroxide that we have in excess is going to be 2.75 times 10 to the minus 3 moles of hydroxide, right? So we know how much hydroxide we now have in excess. We put it into the volume that we have, which is going to be 47.5 milliliters, or 0.0475 liters, and we use that to find our concentration of hydroxide. So, 2.75 times 10 to the negative 3 divide, nope, that didn't work, did it? 2.75 times 10 to the negative 3, there we go, divided by 0.0475 gives us 5.79 times 10 to the minus 2 molar. That's our concentration of hydroxide. And so our pOH is going to be the negative log base 10 of this number. So our pOH is going to be 1.24, and our pH is going to be 14 minus that. There we go, 12.8. Okay, so when you are operating under conditions where you have a weak acid, but you've added more base than the acid that you started with, then you are in a regime where all you need to consider is the amount of excess hydroxide. So that's how you do this kind of problem. Any questions on this one? Okay. Let's see. How do we choose which components to make a buffer? Okay, so remember that the buffering action comes from an equilibrium, an acid-base equilibrium of this type. And so in order for us to have an equilibrium, what we need are a weak acid and its conjugate base, or a weak base and its conjugate acid. We need to have both sides so that whether we are adding acid or whether we are adding base, the equilibrium can shift to compensate. So choosing components to make a buffer is about figuring out what an acid and its conjugate base are that you need. So in this case, we have carbonic acid, and then we could have something like sodium carbonate that is added. Now, how do we know which acid-base pair would be a good one to use? Well, for that, it's instructive to look at the Henderson-Hasselbalch equation. Remember that this is pH equals pKa of the acid plus log base 10 of the conjugate base concentration over the weak acid concentration. And we are in the buffer region when these are close to each other. And so if they are equal, it is 1. So log base 10 of 1 is 0. And so the pH is the pKa in the middle of the buffering region. So what that means is for whatever pH you are trying to make a buffer for, you look for a weak acid that has a pKa that matches that pH, or is at least very close to it. That's the general idea of how to choose what components to use to make a buffer. Any clarifying questions on that? Okay. All right, coupled equilibria. Tracing the, one of the, in the post I put up on what we know about the exam so far, I have a topics list up there, And one of the topics was tracing the effects of perturbations through coupled equilibria using Le Chatelier's principle and the common ion effect. So, and there are questions about, how do we use Le Chatelier's principle and the common ion effect to do this kind of thing? So let's go through an example that we talked about a little bit last week. I think it was last week when we introduced coupled equilibria. And it's also relevant to the small group activity that we had, where we have CO2 as a gas in equilibrium with CO2 that's dissolved. CO2 that's dissolved can react with water to form carbonic acid. Carbonic acid can perform its standard acid reaction so that we have HCO3 bicarbonate aqueous plus H3O plus aqueous, and this should be a minus, HCO3 minus aqueous can do its standard acid reaction, equilibrium with the carbonate ion, CO3 minus aqueous plus H3O plus aqueous. Okay, so when you have coupled reactions of this type, and they're coupled because there are species in one reaction that are also present in another reaction, and so affecting the concentration of these other, of one species in one reaction affects the others. So let's see how we can trace what happens. Suppose we implement a perturbation where what we are doing is increasing the pressure of carbon dioxide that we have. So an example of this might be something like the increase in carbon dioxide that is present in the atmosphere over the last several years or several decades, and what effect that has on the buffering system in the oceans. So if this goes up, then the reaction shifts in this direction to counteract that, meaning that the CO2 concentration in solution is going to go up. Well, if it goes up here, then that means it's going up here as well, which is going to shift the reaction, this way, meaning we're going to end up with more carbonic acid in solution. Well, if more carbonic acid is going into solution, then that is going to shift this equilibrium this way, and so the amount of bicarbonate is going to go up and the amount of H3O plus is going to go up. Down here, that means this is going up, but this is also going up. And so then it's not all that clear which direction the bottom one is going to end up going. You would have to know more about what the original amounts of these two were to see which one has a larger percentage change. And so generally you would expect that if carbonic acid is the only source of hydronium ion that's showing up, then you're going to have equal amounts of these two, which means that they go up by the same amount, both in terms of percentage as well as in terms of absolute amount. And so this equilibrium down here wouldn't shift much. There were probably some some Newton questions you might have seen where you were looking at what happens when you have a diprotic acid and you calculate the first equilibrium to figure out what the pH is that results from that. Then you look at the second one and you find that the concentration of this, the conjugate base, ends up just being a result of the Ka that you had. So whatever the Ka for this reaction was, that ends up being this concentration because these two were the same and so they ended up canceling out. If we write the expression here, Ka equals concentration of CO3 minus concentration of H3O plus over concentration of HCO3. Well, if these two concentrations are the same because both of them are being produced here, then those two cancel, and the CO3 minus, just 2 minus, ends up being our Ka. So I find when I'm trying to trace the effects of perturbations through coupled equilibria that drawing arrows like this really helps me see what's happening. So whatever the perturbation is, you show it. What does that do in terms of a reaction, affecting the reaction? Le Chatelier's principle moves away from the increase of CO2. That makes this go up, and then you just follow the path through. Any questions on this kind of analysis and how you would go through it? Okay. So the rest of the questions that I found on Piazza were all related to solubilities, KSPs, and so on. So let's go through and let's talk about, I guess, the conceptual ones first, and then we'll come back and do the calculations of it. So saturated, supersaturated, and unsaturated. Wait a minute, hang on. I feel like we skipped something. Yeah, there's a question I prepared some stuff for, but somehow it's not on this list. So there was an acid-base question about indicators and about about indicators with multiple color change regions. And so I wanted to show you some pictures that represent different indicators in order to try to address that. So I think this may be the figure that is in the online textbook. And so we see that there are color changes that happen over pH ranges for each of these indicators, but this one in particular, thymol blue, has two color changes that happen. So it's important to realize here that these are just showing the color changes that happen. In between here and here, it's yellow all the way across, and then it changes to blue, and then it's blue from there on out, and it was red all the way up to here. So I actually, even though this is the one in the textbook, there are a couple other ways of representing this that I actually like a little bit better. So this is one way that you can look at this information where it shows what the colors are over the region and then shows kind of an intermediate color when it's in the middle of transitioning. Or you could even look at it this way, where it actually shows very clearly the intensity of the color and how it changes over regions. This one's particularly interesting because you notice all of these are natural components that can act as indicators. So cabbage in particular, red cabbages in particular, is a very common indicator to use in kind of home experiments because there's a transition in this pH range, there's a transition in this pH range, and another one up in this pH range. So you can have a bunch of different transitions in a single type of indicator. Okay. Any questions on indicators before I do go on and talk about the solubility and KSP questions? Okay. All right, so let's talk about some of the conceptual aspects. Somebody wanted a brief review of saturated, supersaturated, and unsaturated. So the idea of these is that there is some maximum concentration that you could get. So if we have the concentration of sodium chloride in water, there is going to be some numerical value for that, some number that you have for that at a particular temperature. We will call this the we'll call this NaCl max. If our actual concentration is equal to that max value, then this is a saturated solution. If our actual concentration is less than that maximum value, that is an unsaturated solution. If our actual concentration is greater than that maximum concentration, then it is a supersaturated solution. And so this is the only real criteria that matters here, is how the actual concentration of your sample compares to this theoretical maximum you can have. Generally, you can tell that a solution is saturated if you have some solid sitting at the bottom of your flask. If you have some solid sitting at the bottom of your flask, then that solid is in equilibrium with the dissolved portion, and so you know that you are at saturation. Now, there being some at the bottom of the flask is not a requirement for it to be saturated, because you may have made it saturated and then filtered all of the solid away. So you can, in fact, have a saturated solution without solid sitting at the bottom. It's just that if there is solid sitting at the bottom, then you know you are saturated. The last remaining question is, how is it possible to have a solution that is more concentrated than this theoretical max? And the answer to that is that this happens in an unstable way, so that if you disturb the system in some way, then the excess will precipitate out very quickly. So you could drop a seed crystal into it, maybe you shake the system, shake the flask, and a little bubble forms, and that bubble acts as a nucleation site for the excess to come out. So this is something that happens. You have to be very careful in order to generate a supersaturated solution, and it's unstable when you have made that. Okay. Let's then talk about this question right here. So apparently there was a Newton question that was asking about if you have a dissolution reaction that is at equilibrium, how can you make more precipitate form? And so some of the answers were to change the temperature, or to add more solid to the system, or to add more ions to the system. And so let's think about what's happening in each of these cases. So if we have NaCl solid in equilibrium with Na plus aqueous and Cl minus aqueous, let's think about what's going to happen when we do each of these kinds of perturbations to it. So the first one I mentioned was changing the temperature, if you want to have more precipitate form. Well, remember that when we change the temperature, we think of Le Chatelier's principle in terms of there being heat on the reactant side if it is an endothermic reaction, and heat on the product side if it is an exothermic reaction. So if we raise the temperature and it's an exothermic reaction, then that will indeed create more of the reactant, meaning that you will get more precipitate. But if it is endothermic and you raise the temperature, then more is going to dissolve, because it's going to go the other direction. And the issue is that some of these dissolution reactions are endothermic and others are exothermic. So raising the temperature will not have a uniform effect on the position of the equilibrium as you look at different substances. So that one can't be the case. If we add more solid to the solution, why doesn't that cause more precipitate to form? Well, if we look at our equilibrium constant for this particular reaction, this is what it is. And notice we do not include the NaCl solid. So adding more solid doesn't affect the equilibrium at all because the solid doesn't participate, it is not part of the equilibrium constant expression. It doesn't change anything. So that's why it doesn't form. So the only way that you can get more precipitate to form is to add more of one or both of these ions, which will then cause it to precipitate out. So if we have this solution and then we added some potassium chloride, for example, then due to the common ion effect, the extra chloride that dissolves will cause this equilibrium to shift towards the left and get more precipitate that comes out. Okay. Does KSP affect the amount of precipitate formed? So I think the question there was asking about almost the same thing, which is, shouldn't the amount of solid that's present affect the equilibrium in some way? And the answer is no, it doesn't. The KSP doesn't tell you right off the bat how much precipitate you'll have. Now, if you know how much of the ions you have, and you determine that you're above that saturation point by using the value for KSP, then all of it that is above that equilibrium amount is going to precipitate. So you can use the KSP to find the amount of precipitate that's formed based upon how much the solution can hold. But I don't think the spirit of the question that was asked is really asking that aspect of the question. So it's important to think about what it is that KSP tells you. It tells you how much will be in solution. It doesn't tell you how much solid you will have, except as it has to be the amount left over when you look at how much can be in solution. Okay. I'm going to go to this one next because there's a table I put together that I think is going to be useful for some of the others. And the question was, is there a trend for how fast certain metals will precipitate with halides? So that's an interesting question. I'm a little curious about where that question came from, but it can lead us into some interesting aspects. The first thing I'm going to do, though, is I'm going to ignore the question fast, because that sounds like a kinetics question, and we haven't talked about speed of precipitation in any sense in this class, and that's a quite complicated topic, so we're not really going to go into speed. So I think what the question is probably asking more about is about at which ones will come out at low concentrations, which ones will come out at higher concentrations, and so on. So I tried to go find a table that has the halides and then a variety of metals, and then determine what their KSPs were for each combination so that we could look for some trends. And I was utterly shocked to find that nobody seems to put this data together in this form, because it seems to me to be a very natural form to put it in, and it will summarize a lot of information in a very concise way. So I spent about an hour this morning making this table to try to answer this question and see, are there some trends? Because I thought that would be a cool thing to look at. And so for most of these, I was able to calculate the KSPs. These are all at around room temperature, 20 or 25 degrees roughly. The berylliums, I had some issues finding them. It just says very soluble and highly soluble. And for the iodide, it reacts. So we can kind of ignore the beryllium part here. And so I have put here, oops, no, all the way down to that. And then these. So these are the alkali metals. So the group 1, these are the alkaline earths, or group 2. And so we probably should just look and see if there are trends within each of these groups separately, because there's going to be something very different between between the top half and the bottom half. And what I kind of see here is that there don't really seem to be any standard trends. So like if we look at the fluorides, as you go down the periodic table here, they get more and more soluble, but that's not necessarily true here for the alkaline earth. So it gets less soluble and then gets more soluble. For the chlorides, it goes down in solubility and then back up. This one here goes up and then down. This one goes down and then kind of seems to stabilize. This one goes up and then down. This one goes uniformly down. This one goes down and then back up. If we look across this direction, we see that the fluorides are all the bottom ones. They're all the least soluble of any of them, except for 3 of the alkali metals, where they are actually higher than the others that are over here. So I don't think that there are really any trends that seem to be obvious from these. And so the point here is that for these kinds of questions, you really need to be looking at treating them as individual pieces of data rather than as trends. Okay, so that's going to be this question here. But we're going to now use this for some examples to look at some of the other questions. So for example, how do you determine which solid from a solution will form first? So let's come up with an example here. So let us see, let's suppose that we make a solution of calcium chloride, okay? And then we make another solution of, let's say, rubidium, no, we'll do potassium fluoride. And then we mix the solutions together. Okay. So what I did was I picked one substance here that has a relatively high solubility, and I picked another substance here that has a relatively high solubility. And then we mix them. And what that means when we mix them is that we have, sorry, this is CaCl2. That means we have some calcium 2+ ions floating around. We have some Cl- ions floating around. We have some potassium ions floating around, and we have some fluoride ions floating around. And so what we need to do then is look at all the possible combinations and see which one has the lowest solubility product. So we've already looked at these, the pairs that we started with, putting them together. So we look at the cross pairs. So potassium chloride. Let's see, potassium chloride right here, its solubility is a bit lower, so that one might come out. Calcium fluoride, oh my goodness, that is tiny. Calcium fluoride has a tiny solubility product. And so that means not much of it can stay in solution. And so calcium fluoride is going to precipitate like mad from this. We mix these two together, and that's going to be coming out. So that's the general approach that you use when you're trying to determine which solid from a solution is going to form first. You look at the combinations of the ions that can form, look at their solubility products, and if one of them is much, much smaller than the others, then that's probably what's going to come out. If there if they are close together, then you might have to look at the actual concentrations that you have and check each of the combinations to see, am I at saturation or above saturation? Okay. All right. Let's see. How do you predict if something will precipitate? So that's actually just what we were talking about right here. So the general idea, so in this case, we determined that calcium fluoride is going to precipitate. The general idea is for a combination. You look at the solubility product, and you write down its solubility product expression. So Ca2 plus F minus squared. If you have concentrations for these values, you plug them in. Now remember that this is only true at equilibrium. Okay. So if you have experimental values, or if you have some values that you get from some other source of the concentration of calcium ions and the concentration of fluoride ions, you plug them in and calculate the value that you have here, and that's going to give you a Q. Remember, Q is the same expression as the equilibrium constant, just not necessarily at equilibrium. So this is always true. If you are at equilibrium, then Q equals K. Now, if you do this for the values you have for calcium and fluoride, and you get a Q that is larger than K, then that means you have too many ions in solution, and so the excess will precipitate. If Q equals K, then you are at saturation. If Q is less than K, then you are unsaturated, and nothing will precipitate. And this analysis here is nothing special about solubility. This is how you determine which way an equilibrium will shift for any equilibrium. It's just that we are talking about the specific case right now about the solubility equation, CaF2 solid in equilibrium with Ca2 plus aqueous plus 2F minus aqueous. So this analysis is nothing new. It is just applying the concepts of comparing a Q to a K to the question of solubility. Okay. So that's how you predict if something will precipitate. How do you determine the concentration of ions remaining after precipitation? Well, after precipitation, you're going to be at saturation. Q is going to equal K, and so you calculate the concentrations straight from the equilibrium constant expression that you have. That's all you do. You write down that expression, and you have some information. You should have the equilibrium constant, and if you know, for example, that the calcium and the fluoride came just from this reaction, if that's their only source, then you know it's going to be this will be x, this will be 2x squared, and so you figure out what x is. Or if you are doing something like this, where you are combining two solutions, and so you know what your initial concentration of calcium was and your initial concentration of fluoride was, then you do an ice table. And so you're going to have a lot of it precipitate out of solution, and you'll find out how much is left. Would you guys like me to go through a quantitative example like that, where we put in actual numbers for this? Okay, happy to do so. So let us suppose that we have, I want to pick numbers that aren't going to be too ridiculous for these. Let's suppose we make a solution that is 0.1 molar in calcium chloride. And we have another solution that's 0.1 molar, excuse me, in potassium fluoride. Let's say we take 100 mils of this, and we take 100 mils of this, and we mix them together to make a 200 milliliter mixed solution. And we want to know both how much calcium fluoride is going to precipitate, and also how much is going to be left in solution. Okay. So our question is, how much, okay, first, our first question is what precipitates, which we already answered. Second question is how much of it precipitates. And then our third question is what are the remaining ion concentrations? Okay, so I'm going to leave that as the problem statement page, and I will start on a new one. So the first thing I would do is I would write down all of the reactions we're going to care about. So CaCl2 solid is in equilibrium with Ca2 plus aqueous plus 2Cl minus aqueous. And we have a K1 of calcium chloride, 1.2 times 10 to the third. We have our second source reaction, Kf solid in equilibrium with K plus aqueous plus F minus aqueous. Our K2 is going to be 20.8. Okay. We have two cross reactions that we could consider. So we have KCl is in equilibrium with K plus aqueous and Cl minus aqueous. Our K3 is going to be, oops, hold on, I put the wrong one here. This is KCl, so 20.8. This one was, excuse me, 308. And our last one is calcium fluoride, equilibrium with Ca2 plus aqueous plus 2F minus aqueous. And our K4 for this one is 3.9 times 10 to the negative 11. Okay, so that summarizes all of the information that we have. So let us start by determining the concentration of each ion in our mixed solution. So we start with 100 milliliters of calcium chloride. We have our concentration, which is 0.1 mole of calcium chloride in 1 liter. Now I'm going to skip a step here and I'm going to put it over 1,000 milliliters, which is another way to write 1 liter. And so we get 0.01 moles of calcium chloride, which means that the amount of calcium that we have, so number of moles of Ca2 plus is 0.01 moles, and the number of moles of chloride that we have is 0.02 moles, because there are 2 chlorides in each formula unit here. Now we also have our potassium fluoride. The calculations, the numbers are going to be identical. So our number of moles of potassium, 0.01 moles, and the number of moles of fluoride, this is a 1-to-1 compound instead of a 1-to-2 compound, is 0.01 moles. Okay. So we have that many moles they are now in 200 milliliters. So our initial concentration of Ca2+ is going to be 0.01 moles over 200 milliliters. And we need 1,000 milliliters to make it a liter so that we can turn this into molarity. And so .01 divided by 200 times 1,000. And we get 0.05 molar in calcium 2+. And let's think about that for a moment. We started with 0.1 molar, and it is now diluted by a factor of 2. So if you were really thinking ahead, you could have jumped straight ahead to its concentration being half of what it started being. So all of these steps that we have gone through are the correct steps to do, but in cases where the numbers line up nicely, you can jump directly to answers in some cases. So using that concept, we also now know that our chloride ion concentration, remember we have twice as much chloride as we do calcium, so that is then going to be 0.10 molar. Our potassium ion concentration, and remember these are our initials concentrations, is going to be 0.05 molar, and our fluoride ion concentration initial is going to be 0.05 molar. Anybody have any questions up to this point of getting to our starting point of what the concentrations are before we consider precipitation? Okay, so what we're going to do now is we're going to look at the cross products. So the two possible cross products are calcium fluoride and potassium chloride. Let's look at the potassium chloride let's see if I can talk. Let's look at the potassium chloride case first. So we look at our KSP for potassium chloride. We wrote over here is 20.8. And that's going to be in units of molar squared. And so our Q for KCl is going to be 0.05 molar times 0.10 molar equals 0.005 molar squared. Our Q is less than our KSP, so potassium chloride will not precipitate. We are below saturation. Okay. Let's now look at the other cross product we have, the calcium fluoride. So we have our KSP for calcium fluoride is 3.9 times 10 to the minus 11. And remember that our expression for this, oh, hang on. Did I do that right? No, I did do that right, okay. Our expression for this is let me write down what it is, calcium fluoride, Ca2+, fluoride ion concentration squared. So let's look at our Q. Q is going to be, let's see, calcium 2+, that's 0.05 molar. This is molar cubed. And the fluoride ion concentration is 0.05 molar squared. So that's 0.05 cubed. And so our Q is 1.25 times 10 to the minus 1, 2, 3, 4 molar cubed. And our Q is much higher than our KSP, and so we know it will precipitate. So that means it's now time for our ice table. So let's write our reaction. CaF2 solid in equilibrium with Ca2 plus 2F minus. Okay, we do that. This we don't do. All right, we have an initial concentration of calcium ions of 0.05 molar, initial concentration of fluoride ions of 0.05. Now our calculation will be easier if we shift the reaction as far to the left as possible. So remember, so we're going to run out of fluoride first because it takes twice as much fluoride as it does calcium to form the calcium fluoride. So we're going to take this down to 0, which means we take away half of this, so 0.025 is what that's going to be. Now, so this is now where we start. We ignore our initial line. We are now going to have our change be positive here. Remember, that has to be 2x because we have 2 fluorides that have to be formed in each case, and we know it's positive because we're starting at 0 and we can't go negative. And so now we end up with 0.025 plus x and then 2x. Now notice that because our equilibrium constant is so tiny, 10 to the negative 11, we expect x to be very small. And so we can neglect it right here. And so we use our KSP, 3.9 times 10 to the negative 11 molarity cubed equals 0.025 molar, we're neglecting that x, times 2x squared. So x squared is going to be 3.9 times 10 to the negative 11 molar cubed divided by 0.025 molar and divided by 2 squared, or 4. So times 4. Let me calculate that out. 3.9 times 10 to the negative 11 divided by 0.025 divided by 4. And we end up with 3.9 times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 to the negative 10. That's x squared. So our x is going to be, take the square root, 1.97 times 10 to the negative, so that was units of molar squared, 1, 2, 3, 4, 5 molar. Okay. Now that we have x, we can start to figure out the answers to the specific questions we were asking. How much of it is going to precipitate? Well, this is going, essentially, almost all of the fluoride ion is going to precipitate. This number here is going to be tiny compared to the amount of fluoride that was actually there to begin with, the 0.05 molar. So we know that we are going to have 0.05 molar fluoride. We have our volume of 200 milliliters. Okay, let me do this differently. We have 200 milliliters. We're going to focus on the fluoride ion. 1,000 mils is 1 liter. We have our concentration, which is 0.05 moles of fluoride in 1 liter of fluoride. We have, for every 2 moles of the fluoride ion, we have 1 mole of calcium fluoride that gets produced. And so 200 times 0.05 divided by 1,000 divided by 2 gives us 0.005 moles of calcium fluoride that are precipitated out. You could convert that to grams by using the molar mass if you wanted to. Let's now look at the remaining question of what are the concentrations of the various species in solution at the end. The calcium ion concentration is simply going to be our 0.025 molar. Our potassium concentration hasn't changed, so 0.05 molar. Our chloride ion concentration hasn't changed, 0.10 molar. And our fluoride ion concentration is going to be 2x. So let me see what sheet I had x on. X is here. So that's we'll just call that 2 times 10 to the negative 5. So it's going to end up being 4 times 10 to the negative 5 molar. Okay. Any questions on how this procedure went? All we are doing here is just tracking the various components and looking at each of the reactions that can happen. It looks like I am at time for today. So looks like there's only one question that I didn't get to. I can do that very quickly because we did exactly the same thing here. Why do we include the 2 in 2 different places, both a coefficient and an exponent in the calculation? Well, we can see here that you get a 2 as a coefficient because as this dissolves, 2 moles of it form for every 1 mole of this. You have the square because the KSP includes that component squared. So that's why you get a 2x squared, because it's happening in both places. It's happening here because of the stoichiometry, and it's coming here as the square because it's part of the equilibrium constant expression. Okay, thank you very much for today. These were some good questions to go over. I think that what we went through here using, in this particular example, was a very good example of the kinds of things I might ask on the exam. So, so this particular example is right in line with what I think you should be looking at. Thank you very much.